Hi, my name is Edward Fish. Today I'm presenting two-stream transformer architecture for long-form video understanding, joint work with John Weinbrand and Andrew Gilbert from the University of Surrey. The majority of video understanding work has tended to focus on short videos, with methods and datasets targeted to applications in action recognition, object tracking, and segmentation. Long form video understanding aims to model long term temporal patterns over thousands of video frames to answer questions relating to the full picture of the video. For example, what is this video about? Who are the main characters in this story? What is the relationship between them? Whereas short video understanding has applications in object tracking, action recognition, and segmentation, long form video understanding tasks include video recommendation, archiving, and retrieval systems, allowing users to find and query content based on theme, aesthetic, genre, or story. Working with long videos, though, can be challenging, and there are currently few datasets and methods available for long form understanding tasks. For example, action recognition datasets in general have clips from about 2 to 10 seconds in length with thousands of samples, whereas long video tasks are defined as above 1 minute in length. This not only has implications on the memory efficiency of long video networks, but it also means that they're data inefficient, requiring thousands of frames per single optimization step. With this in mind, long video networks should be both memory and data efficient, able to learn from fewer optimization steps and a limited number of labeled samples when compared to uh, action recognition and object tracking architectures. So, intuitively, an image can provide a good summary of a moment in time, and so it's logical that image CNNs perform relatively well at classifying short videos from only a few frames. However, finding ways to temporally aggregate these features over longer periods is more challenging. Adding temporal modeling of CNN features via recurrent networks, for example, provides one solution, but these architectures suffer from computational efficiencies due to their recursive design. While 3D convolutional approaches also do not scale effectively, primarily due to their high computational footprint and the linear growth of the receptive field in the temporal dimension. More recently, vision transformers have been adapted to the video domain, achieving state-of-the-art results on multiple short video tasks. But it's been observed that transformers are not as data efficient as their CNN counterparts, requiring more data and time to train. And these issues are only exaggerated in the long video domain, as although we have lots of data, we have a limited number of samples to perform gradient updates. We then propose to answer the question, how can we leverage inductive bias from image CNNs to make video transformer networks more data and memory efficient for long-form video understanding tasks? Our solution is a simple two-stream architecture that models dependencies between high-resolution frame embeddings, which are sparsely sampled, and low-resolution temporal context embeddings, which are sampled more densely. Our contribution lies in the sampling methodology and how we scale this simple architecture to train on videos over 2 minutes in length on a single GPU and in just a few hours. For sampling, we first analyze the video for changes in average frame intensity and brightness using a run average over RGB video channels. We set timestamps as scene segmentation points and uniformly sampled 12 frames from each scene. The 12 frames are used to generate a low resolution temporal feature token via R2 plus 1D 3D CNN encoder, which is pre trained on Kinetics 400. We also extract the central frame of each scene at a higher resolution and use a lightweight ResNet 18 CNN pre trained on ImageNet to obtain a spatial feature token. So for each scene in a long video, we now just have one temporal and one spatial embedding, which represents the spatial and temporal content of the individual shot or scene. In comparison with a pure transformer architecture, such as Vivid, we'd require around 108 tokens just for one scene, making long video understanding unfeasible in memory-constrained settings. After we've obtained a spatial and temporal embedding for each scene, we can then model the temporal dependencies between them and train for a number of downstream long video understanding tasks. For each stream, we share positional embeddings and use a randomly initialized classification token, which learns a representation of the content from each stream. Three-layer MLP for each stream projects the spatial and temporal features to a shared embedding size, and these embeddings are then concatenated and then projected once more for video classification downstream tasks. The loss function is simply a binary cross-entropy loss between the projected concatenated features and the task label. During training, we backpropagate via both the spatial and temporal encoder, but we do not update weights in the temporal CNN, and this enables to process over 2 minutes of video per single backwards pass on a single GPU. Since we don't backpropagate via the temporal CNN, we can also extract the features before training, reducing the model processing requirements to just one frame per scene if required. So we evaluate the method on two long-form video understanding datasets. First, we show state-of-the-art performance on the MMX Trailer 20 dataset, which is a multi-label genre classification tasks on film trailers, which contain 2-minute videos with multiple scene viewpoints and actions. We compare with a number of methods for extracting and aggregating CNN features, such as LSTM's i3D and temporal pyramid networks. Due to the length of the videos in this dataset, we can't compare with current video transformer networks. We also provide results for stand large, in which we also train the temporal CNN, and this leads to a 15% improvement in accuracy over current methods. We also evaluate the method on the long video understanding dataset for tasks including relation identification, speaker recognition, and scene classification. Our method outperforms current transformer methods, including the recent object transformer, which requires masked self-supervised pre-training and models complex interactions between people and objects throughout scenes. It also outperforms other video transformer networks such as VideoBert. In our ablation experiments on the MX20 dataset, we demonstrate the data efficiency of our setup, where the small network can be trained on just 2,000 videos while only losing 3% accuracy. We also experiment with different fusion methods, including a gated network, which selects which stream to use for each task, and a layer-wise knowledge distillation setup, where the spatial stream learns from a temporal teacher transformer. Interestingly, basic concatenation and linear projection provides the best results. Thanks for watching this presentation. The paper and code can be found at the links.